Welcome back to ECE 220. This is our last time as a class in this lecture scenario. Tomorrow you will not have class. That's one of the off days based on you doing your labs in this course. So you're given those days off, and tomorrow is the last one that we're exercising that way. Don't forget, homework number 15 is due this evening, and teacher course evaluations are due at the end of tomorrow. I wouldn't suggest you wait that long, but that's when they are due. And teacher course evaluations are very helpful for me to understand what worked, what you think could be improved, etc. in the course. I've also posted a few additional times for office hours for the rest of the semester. They don't finish on the last day of class, which is tomorrow. We'll have the normal time then. We'll have the normal time on Friday, 11 to noon. And then I guess Monday is normal, but the others are a little different. And the last day before our final is next Thursday. The last day before that, on Wednesday, I'll have 2 hours of office hours in the morning from 9 to 11. Hopefully that spans a gap if you do have final exams at the 8 o'clock hour and the 10:30 hour. You'll have a 30-minute window. And if those times don't work, let me know and we can see about scheduling something outside of those scheduled office hours. Today I was planning to go over the practice final exam from fall of 2016 that Dr. Marcelin has provided on his website. And if you're looking at that exam, you'll notice that half of the problems are from material after exam number 4. You definitely then need to be very comfortable with Chapter 9 material, which is sinusoidal steady state, dealing with phasor analysis, ideal transformers, etc. And I'm going to now attempt to work through some of those 24 problems. I don't think I can get through 24 problems in 50 minutes, especially now that I've used up 2 of those minutes with information. But are there questions before we start? And what I've tried to do, and I don't know if I'll be able to follow my script, but I've tried to now mix up which ones I'm going to go through. I'm not going to just start at the beginning and work through, because it may not be the most challenging for me to start at the beginning. So let's see if we can work through this in a way that is helpful for you. And now I have multiple numbers that I have to sort of look at to try to figure out what I'm doing. But now let's look at problem 20. This is in the second half of that final exam. And this one is dealing with sinusoidal steady state, but it's already now transformed into the scenario where you're dealing with complex impedances and phasors for your sources. You're given now an independent voltage source. You have a dependent current source, and that current source is dependent on the capacitor's phasor voltage, V sub x, and you're asked to find the voltage phasor across that 2 ohm resistor. That's the question. And you'll have 2 hours to work, not this question, but the entire exam. So you'll want to make sure and allocate your time appropriately. The first half, 12 questions, and I didn't read the first page of the final exam closely, but I'm guessing it's going to be consistent with what we've done before. The first half will be worth half as many, and part 2 questions are worth twice as many. So you'll want to make sure that you do better maybe on the second half, since that's twice as many point values, and that's why I'm focusing on those here. How would you, and there's many different ways of solving this. What's one way? Yes, I know I'm looking now at Mr. Mesh Analysis, but I wouldn't recommend that in this case, because you have three meshes. One of those is actually determined by your dependent current source, but you can hopefully see that you have that common node, and now in fact all of those share the same node, and that's the unknown that you're trying to find, which is the voltage phasor V. Meaning, if we can now write a KCL equation with respect to that node, we should be able to maybe find our way towards determining that phasor voltage, that node voltage, which now is a phasor. We need to find this current, that current, this current, and that current, which is actually specified as a dependent current. Let's now sort of work our way from left to right in terms of those currents doing the KCL. What's this current right here? Let me, do I want to label these? Suppose I call that I1. What's I1? In terms of the voltage phasor we are trying to determine and any of the other variables in the circuit. Do you see it's where we are at? And I'm going to overbar. That's just more convenient for me, but that's the same as this. That's that voltage. So I'm calling this the value of the voltage I'm trying to evaluate for, minus this given source voltage, and I'm not even going to say at an angle of 0. I'm just going to keep it as real. So now it's basically in polar form or rectangular form because it has 0 angle. And now I need to divide by the impedance that drop is across. And that's now 1 plus J2. That's I sub 1. If we call this one I sub 2, I would say forget V sub x. If we can avoid it, let's not mess with it. So I'm going to say that's V bar. I sub 2 is V bar divided by 3 minus J5. I haven't introduced another unknown, is why I'm avoiding worrying about V sub x underbar. But you could have, I guess, said V bar minus V sub x divided by what? 3. And that would be the same current. But now we have that V sub x in there as well. Let's now look at I sub 3. That one's fairly clean. That's just Ohm's law. And with a resistor, that's V over 2. And then we have the fourth current, which is going in the opposite direction. And now I do have to call that what it is. I don't know anything more than it's now minus 3/4 V sub x, and that sums to 0. But can I find V sub x? Ideally, I would want to find that in terms of V and the given sources. Do you see that V sub x is really just a percentage of V? It's a voltage divider. V is divided across 3 and minus J5. V sub x is just the piece across minus J5. So you could find the current I sub 2, which was, we just found that. So you could say this many different ways. You could say, oh, it's minus J5 times that I sub 2 bar. Or you could say, oh, that's actually a voltage divider. It's minus J5 over the total impedance times the voltage. It's the same expression. This was Ohm's law, and this was voltage divider. But they both yield the same result. Now what we need to do is put this in there and solve for V. It's just tedious, but you can do it. It's just keeping track of all of the complex numbers. You will now have this piece moved over to the right-hand side. You now have some mess of complex numbers scaling V equaling 33.8 over 1 plus J2. And that's a complex number. If I carry it through just a little bit further, I will now have 1 over 1 plus J2 plus 1 over 3 minus J5 plus 1 over 2 minus 0.75 times minus J5 over 3 minus J5. All of those are scaling V. And then that equals 33.8 divided by 1 plus J2. That's just some number. And you can divide both sides by that complex number and solve for V. So this is going to get you doing your complex number gymnastics. Pardon? Where did the 33.8 come from? That was this moved over to the right-hand side. That was what the source was driving our system with. So unbeknownst to us, we had some sinusoid, a cosine of magnitude 33.8 that was exciting this circuit. And if you do that, you will end up with, or you could say it's obvious that the answer is 8.8 minus J60. Maybe you can see that. I can't, but maybe you can. After doing all of that complex algebra, that's what you end up with. Questions on problem 20? Pardon? Can you plug that in? To some calculators you can plug that in. You can plug that in, what's in the square brackets, and it will do the complex algebra for you. You now divide that into this other complex number, which is 33.8 divided by 1 plus J2. If it doesn't work for you, then you'll need to start converting all of those in the square brackets probably to rectangular form. Now you have a real part and an imaginary part. I would then convert that to polar, divide by that polar form, and then the 1 plus j2 I would probably convert to polar. And now you have, unfortunately, your answer is expressed in rectangular. You'll have to now back out the polar answer into a rectangular answer. Question?
When doing like complex transformations into the phase of the polar form, do you recommend like how many decimal places should we always use?
So the question was, when we're converting back and forth, how much accuracy do we need to maintain in order to obtain the eventual answer? So if the answer that I provide is 2 decimals, then I would carry about 4 significant digits through your algebra. And then the rounding hopefully will allow you to end up with something very close to what the answer is providing. And if you now have something like, well, hopefully your answer, if you do keep 4 significant digits, you should end up with the answer given in 2 significant, maybe even 3 significant digits. Other questions on problem 20? Actually, I thought another good one would be to continue sort of in that same thought process, staying with complex numbers, and look at this question. Here they're asking for you to find the current through that middle inductor. And again, the answer is going to be expressed in rectangular form. You may end up with it in polar. You'll just have to make sure you convert it into rectangular form and match it with one of the answers. How would you solve this? You could do superposition, correct, and that's really what you're doing even if you do it all at once. But I actually was going to do it all at once, and I was going to actually do mesh analysis for a change. So if you do it, and I'm going to do mesh analysis a little differently than what I've done before, I'm going to say, you know what, I'm not going to negate that. I'm going to just call that one of my mesh currents since it's given. And then I really only have one unknown mesh current, even though there's 2 meshes. I'll call this one I1, and this one I will call I sub 2. And my eventual answer, I underbar, I will probably overbar my phasors. Is that okay? When I create the exam, is it gonna, I hope it doesn't confuse you. Ask if it's not clear. But now I is going to be eventually I1 plus I2, and I already know what I2 is. It's 3 at 90 degrees. I now just need to find I1. And the logical way to look for that is to write KVL around the left mesh. And that says I now have minus 2 at an angle of 0. I'm not even going to carry that through because if I need to add and subtract, it's in polar, it's in rectangular because it has 0 angle, plus 2 times I1 plus J2 times, here's where I have to pay attention to how I've labeled my currents. It's typically I1 minus I2, but they are both helping each other. In this case, it's I1 plus I2. And that's equal to 0. I2 is given. That's 3 at 90 degrees. So if I start combining terms or coefficients for I have 2. That's that one. And then I have plus J2, and that's I1 bar. I've now accounted for this piece. What is this combination? I now have J2 times 3 at 90 degrees. It's another way of writing that. Or is there? What's 90 degrees? There's J. We're standing on J. That's just J3. We now have J2 times J3, or J squared times 2 times 3, or J squared 6. So this is now J2 times J3. That's J quantity squared times 6, and J squared is minus 6. That minus 6, which I obtained from J2 times I2, I'm going to put on the other side, and that will end up then, along with this minus 2 on the left, gives me 2 on the right, and the minus 6 on the left gives me 6 on the right. And you're going to see this quite a bit, maybe. Real part and imaginary part equal values, maybe with a negative sign, but this is now a right triangle, 2 over and 2 up. The hypotenuse then is that side times the square root of 2. And what's the angle? I've gone the same distance over as I've gone up. The angle is 45. This I can fairly quickly write without the calculator as 2 times the square root of 2 at an angle of 45 degrees. And now I can solve for I1. What's my angle? I now have this angle, which is 0, minus the denominator's angle. But when I was working through some of these problems, I got a little quick and I messed up. You need to really pay attention to what the questions are asking. This one I might say, oh, there's my answer. No, you have to remember this is only the first part of our answer. We actually needed the total current I and not just I1. We now need to add that to I2 to obtain the actual answer. So we now need I, which is I1 plus I2. Or this is now 4 at the square root of 2 at minus 45 degrees plus, and what was I2? That was 3 at 90 degrees. So if you convert those both to rectangular, you can add them up and end up with I. And this one converts nicely. That's just J3. And the other one converts pretty nicely too, because it has a square root of 2 involved. We now have 4 over the square root of 2. And the cosine of minus 45. And I'm now a negative, so I'm going down. And the sine of 45. And now I have a real part of 2. I have a minus J2 plus J3 or a plus J. That's I. And hopefully that's one of the answers. Questions on that? Let's step a couple of questions beyond that one. Let's go to question 23. And this one now is trying to relate phasors from some circuit. And this circuit now has an ideal transformer, and maybe it's playing nice, maybe you don't think it's playing nice, but things aren't labeled. Now it's up to you to label it so that you can work your way through the problem. You need to establish a V1 and a V2 and an I1 and an I2, because this is an ideal transformer, and we need to now be able to establish those turns relationships based on N1 and N2. So I just went ahead and said, okay, I'm going to call this one I1, and I'm going to call this V1. And since I really am trying to find this I, it might be easier for me to say, oh, you know, if I knew this voltage, V2, I just divide that by that total impedance in the secondary side, and that gives me I. So now how do I proceed? They didn't even tell us what V is. How do we work this? They told us V in the diagrams. All of those are the same, so we can just pick one. And maybe it's easier, maybe not. I went a few attempts on this, but I said, oh, let's just say that V bar is the square root of 2 at an angle of 45 degrees. Doesn't matter, but now that square root of 2 is going to be helpful in establishing the relative fraction that I is relative to the square root of 2. We know that V bar looks like it's at a 45 degree angle, so I'm just going to say that's what we'll use. And now we need to find where is I relative to V bar. And I is the secondary current, or the current in the secondary side of the circuit. What's our current turns relationship here? We know that amp turns are equal, and what we now need to account for is the sign. Is it positive or negative? And how do our currents turns ratio, how do we determine the sign? If one is going the opposite of the other, if one is entering and one is exiting, we have a positive sign. What do we have here? They're both entering the dot. I1 is entering the dot. Which is I2, is entering the dot. So we now need to introduce a negative sign into our relationship between currents and turns. You need to be comfortable making those decisions. What about our voltages? Our volt turns, and that's V1 is just V. but let me just say V1 over N1 is equal to V2 over N2. And now what do we want for the sign there? And for voltages, we want the polarities to match at the dots. And here, the way I assign V2, I just flipped it. So I have a negative sign here as well, because my negative terminal on V2 is at the dot. My positive terminal on V1 is at the dot. That says, oh, you need a negative sign in your turns ratio. So now what do I do? Well, let me just continue and say, oh, that current, do you see that that's Ohm's law with V2? We have V2 divided by the total impedance. 1 over 2 square root of 2 minus 1 over 2 square root of 2, J. And we actually want to relate I with V1, and this says that now V2 is minus N2 over N1 V1. Or V2 is now minus 1/4 V1. I can now say that this is minus 1/4 V, that's V1, over this kind of a mess downstairs. Let me just factor out the common factor. And now I have a 1 minus J. And how can I write this in polar form? I go over 1 and down 1, so I'm going the same distance over as down. My angle is minus 45, and my hypotenuse is 1 squared plus 1 squared, square rooted. And it's not maybe clean, very clean, but that square root of 2 cancels that square root of 2 in the denominator. And I now have a minus this 2 in the basement of the basement comes upstairs and cancels the 4 in the basement of the numerator. So I now have a minus 1/2 if you're following my story here, my home story in the basement. But now we have minus 1/2. And what happens to our minus 45 when it comes upstairs? And what do we now have? Wait a minute, did I mess up somewhere? Did I miss something? I is V2 over that. Oh, okay. So now I need to plug in what I assumed for V bar to obtain the actual value for I bar. And what did I assume for V bar? I bar is now minus, and can I take that minus sign, can I handle that, or what does that minus sign do to a phasor? It just moves us on the opposite side of the origin from where we were. Or we could now take that 45 and go negative. Let me just leave it in there for now. I have minus 1/2 at an angle of 45 degrees. And what did I assume V bar was? V bar, I said, was the square root of 2 at 45 degrees. Or I now have a magnitude of the square root of 2 over 2, or half of the length of V, and I have a minus 90 degrees. Or do you see that this is now the square root of 2 over 2 at minus 90 degrees? I can just take plus or minus 180 from 90, and if I keep that angle less than 180, I can subtract 180 from 90 to get minus 90. Or I could say, oh, I was on J at 90. I want to go opposite J because of the minus sign. I'm now down at minus 90. I bar is now down at minus 90, and it's half of half of V. Do you see which one it is? Yes.
So if you were to, see how you move the negative from outside of the angle?
Yes.
If you were to do that first, on the first part, wouldn't you get a 0 for the angle?
So now the question was, if I now move the negative sign, so now the question was, what if you move that negative sign into here? But now you can't just, so maybe that was, how do I want to say that? Maybe it was misleading doing it at the end, but now if I'm at 45 degrees and I want to go opposite to that, do you see that I'm actually over here? So I need to add or subtract 180. So you have to be careful. You can't just slide the negative through, which is what this seemed to do. This sort of said, oh, a negative, you just negate the angle. That's not really what we're doing. We're going 180 degrees away from that angle. So the question was, if I now slid that negative sign through, don't I get minus 45, and then that cancels this 45? So it's not quite that way. So your question is valid. Now if we did this, what would your angle be? And we're multiplying this times the square root of 2 at 45 degrees. Now this is where it started, and then we negated it to get there. So this is where we are at, and so we have 1/2 at minus 135 degrees. And we now multiply that times this, and we better end up with the same answer. So you can take care of the negative sign whenever, but you have to do it properly. You can't just, it's not just a simple negate the angle. It's change the angle by 180 degrees when you push the negative sign into the angle. Great question. Does that help? Yes.
So I see at the very beginning, for V bar, where angle 45 is coming from here for some, but
How did we get the square root of 2? Well, that was, the question was, where did, in the world did you get the square root of 2? That just came out of the air, to be honest. Actually, I started with 1 at an angle of 45 degrees. And then I would have ended up with half of that, but I thought, well, maybe I'm going to see a square root of 2, so I changed it up and put a square root of 2. You can just say it's some magnitude at an angle of 45, because it's not given, is it? You would just say, okay, V bar is some M at an angle of 45. Then what you would look for in your I formula, you would say, oh, I better be smaller than M. Hopefully I has a magnitude of M over 2 or something, because you're saying which phasor diagram can be approximately correct. So you don't know the actual numerical value of that magnitude. You just assume one, and assume one that feels warm and fuzzy to you. I'm not sure I like that square root of 2 now that I've picked it. It's not very warm. I'd maybe change it back to 1. Yes? So now the question is sort of, if I now have a capacitor, you kind of have to play in 2 different rooms. So earlier this semester in Chapter 5, we were saying, oh, let's combine capacitors in series. And how do they combine? Like resistors in parallel. But now when we're dealing with Chapter 9, impedances, you just play with them like they are generic resistors. If they're in series, if it's capacitors, the capacitive nature is accounted for with the sign of that impedance. You just add them up. So if you had 3 capacitors in series in sinusoidal steady state, you just add up their impedances. So you don't make it any more, you don't go back to Chapter 5 and say, wait a minute, these capacitors are in series. No, so kind of compartmentalize and say, wait a minute, what are they asking? So one of the questions on this practice final is a interconnected set of capacitors. And they say, what's the equivalent capacitor? Then you go to Chapter 5 and you say, oh, these are in parallel, these are in series, I need to combine them this way, and boom, here's my equivalent capacitor. In Chapter 9, now we go into a different room and we say, we're in sinusoidal steady state, we're shaking. We now figure out what the impedance is of this capacitor, what it is of this capacitor, and now however they're interconnected, we treat them like generic resistors. If they're in parallel, we combine them as a product of 2 divided by their sum. But we keep track of all the signs in those impedances. Is that clear? That's a good question as well. Any other questions? We are 1/8 of the way through. You will go quicker than this on the final. Okay? Where am I? I was wanting to go. I hope that, yeah, this one I thought you might like to see discussed. This one now has 3 different figures, and it's trying to give you information about what's happening. So here, the box labeled circuit is the same in all 3 of these pictures. I'm going to play with fire here. I'm going to use the capacitive sensing of my tablet and collapse that. So now I have 3 different figures, but in those 3 figures, my circuit box is the same. It's just what's on the outside of that box is being modified in the 3 different cases. When 2 different voltage sources are connected at the terminals, the currents are as shown. So the top one, we connect a voltage source of 100 and we get no current flowing. What's that telling you about the circuit up above? the top circuit. Is it telling you anything? Maybe it's not helping you with anything at all. But it should be. That should be giving you useful information. Now view this circuit as if now you've connected something across the terminals of this circuit, and in fact you've connected 100 volts across it, and there's no current flowing in or out of that circuit. What's that tell you about the voltage dropped across here and here? It's the same 100 volts, right? There's no voltage drop here to push a current. So there's nothing happening there to force a current. There's no potential difference. And for that reason, we could say, oh, our Thevenin voltage of that circuit is 100 volts. What's the second circuit tell us? Now we're in the lab and we adjusted the voltage on the right to a little bit more. We've made it 180, and now we have 4 amps flowing. So now in terms of our circuit, what do we have? Can I go down here? Now I'm saying we've already identified our circuit to possess 100 volts. So here's the terminals of our circuit, and now we've connected. And I would encourage you to draw pictures. Don't try to think it through in your head. Put it down on paper so that you can kind of use most of your thinking power on what's necessary and not keeping track of the details. We now also are told that this is 4 amps. Can we now figure out what our circuit's internal resistance is? We now know that 180 minus 100 divided by R gives us 4. Or we can solve that now for R. R is now 80 divided by 4, or R is 20 ohms. Now we can use this circuit. We've now identified what's in the box, what the circuit box contains. It's 100 volts in series with a 20 ohm resistor. And now it's connected here with a 5 ohm resistor. So now we know this. I don't know why I'm changing that, but it was a DC source, so now it's DC. And we've now attached 5 ohms, and here's 20. And the question was, find the amount of power that would be delivered by the circuit to the 5 ohm resistor in the third figure. So now we need to find the power there. We're going back to, I don't know, first week in September, aren't we? Time has flown. I can't believe we're at the end of the semester. Now I'm getting nostalgic. But what's the power? I squared R. And you can find I. I is now, and it's not even a phasor, is it? We're in DC, we're in resistive circuits. This is now 100 over. So how many quarters are in a dollar? So our current is 4. We now have the power, P, is I squared R. So we have 50 plus 30, or 80 watts. Hopefully that's one of the answers. Are you kidding me? We've done 1/6 of the exam. But it's only 50 minutes. We'll just, and what we've done we've almost answered all of the second part, and that's worth twice as many points. So we just have to focus or just quickly go through the first part. But the next one, let's see, what was the deal here? Oh, 5, finding. Oh, here, yes, I have plenty of time. How do we solve this beast? We now need to find the equivalent impedance between terminals A and B. Oh my gosh. But remember, this is Y delta. Look at the bottom delta. Those three impedances that are in the delta are equal. And in 320, you'll call that balanced. And when they're balanced, now there's just a factor of 3 different between the Y connection and the delta connection. So you can replace that bottom delta with a Y. Where each of these boxes is 2 plus J2. And now you just start doing your complex number gymnastics and combining all of these impedances. You can now combine this in series with that, this in series with that, and then these two are in parallel, and add that parallel to this one and you'll have it. It's just involved, but it's doable. I will stop there. I appreciate your patience with me going over a little bit, but now you've done most of the second part. And if you have questions, I do have office hours the rest of the week before the exam.